For our last speaker, we have Professor Czeslaw Bruckner, also from the University of Vienna. After doing his doctorate at the University of Vienna here, he not only was a fellow at the Imperial College in London and in Beijing at the university, but now he is the director of the Institute of Quantum Optics and Quantum Information here in Vienna, and also a full professor. And his talk will be the Rashomon effect when interpretations of quantum theory disagree. Thank you.
So, good afternoon, or better to say good evening, everybody. As you see, I'm going to talk about different interpretations of quantum theory. I'm a physicist, a quantum physicist, in terms of John Bell, a quantum engineer, or even more precisely, I do what he denoted as his hobby. So, as I see, my role here is just to present you a case study. So we have this theory, one of the really most advanced theoretical ideas of humankind, and yet we are not sure what it really means. So before I explain why I entitled my talk in this way, I want to reveal a very deep truth. And this is what is really the most widely accepted interpretation. So if we set the stage, then we can relax. I can even argue that 99% of all physicists and quantum physicists agree on this interpretation. And this interpretation is shut up and calculate. So I just want to put the scale where we find ourselves. This is a talk about the rest of 1%. And it's really a remarkable achievement of Flavio and his colleagues, students, that out of this 1%, they could motivate that many people to fill this lecture hall. And actually, I don't remember that this lecture hall was that filled even on balcony. So I really congratulate for this. So now about the title of the talk. So it's called the Rashomon effect. It originates actually from the movie directed by Akira Kurosawa in 1950. And this is a movie that has a plot that consists actually of 4 stories. What we know that there was a crime committed in woods, and what we see are 4 different stories. The story, the wife story, the samurai story, the bandit story, and the wooden cutter story. And what is interesting that they apparently all describe the same event, but not only that they disagree on what happened, they even these stories mutually exclude, they are contradictory. So you cannot extract out of this a consistent, coherent story what really happens. So what happens at the end? I don't know. And the question is whether it is possible to extract a consistent story out of this. So this resembles exactly the situation as we know in quantum theory. We have this theory, there is a unique formalism. We know how to apply this. And even the success of our technology in terms of laser, nuclear power, in terms of GPS and all other inventions, chemistry, semiconductor industry, confirms that we very well know how to apply this theory, and that there is no consensus among the experts what the theory really means. So that's why we have many different stories, many different interpretations of quantum theory. So our wise Dean actually already quoted David Mermin, and I put here another quote, more recent quote from 2012 from his Physics Today paper, where he says quantum theory is the most useful and powerful theory physicists have ever devised. Yet today, nearly 19 years after its formulation, disagreement about the meaning of the theory is stronger than ever. New interpretations appear every day, none ever disappear. And I counted in Wikipedia, and found there are actually 17 interpretations. The last point in this list is other interpretations, suggesting there are many more. So what is really the problem? The problem is that we are not sure what is the map between what I will call symbolically as a world, nature, and the mathematical symbols that we use in the theory. And here is just symbolically this psi function. We already heard in the previous talk about the psi function. So this is according to quantum mechanics, the complete description of the experimental situation. That's what we deal with in quantum theory, but we don't know really the connection between the two. So we don't know what it really means when we write down a psi and associate to a certain system, what it really refers to. And I will be more specific in a short. So what is the meaning of the psi function is the question here. And in order to really put in contrast different interpretations, I need to present you the most simple experiment that we can perform in quantum theory. So what you here see is a particle. It's a photon or a neutron or an atom. Then you have a half-silvered mirror. Half-silver mirror has this property, that's for non-physicists, I'm sorry for physicists, has a property that if you shine a light on it, then half of the intensity of it will be reflected and half of this will be transmitted. And what I have here are detectors, photodetectors, detector plus, that detects all the light that goes through the mirror, and the detector minus that detects all the light that will be reflected. Now imagine that I, instead of light, use a single quanta of light, a single photon. And I send it to the mirror, and what happens is something like that. Sometimes the detector plus will click or register the photon, and sometimes detector minus. And all what quantum theory tells us, or the psi function, it predicts actually only probabilities for the individual outcomes. So the core of the lack of consensus among the quantum physicists what the theory means is actually the probability and the randomness. Because the quantum theory, all what it predicts are probabilities. Never it can tell you what will happen in a single run of the experiment. Well, then there are these two groups of interpretations that we can actually distinguish with respect to the question of the notion of probability in nature. And the first group, or camp, I will call interpretations about reality, and I will very shortly be more specific about that. And the other group is about knowledge, and there are different interpretations. I put here Bohmian mechanics that we just heard from Professor Bertelmann. Then I put many worlds. Well, objective collapse models are not really interpretations, but I come to this point. And then about knowledge, Copenhagen, relational interpretation, or something which is very modern, quantum Bayesianism, or cubism in short. Now, what I mean with about reality? With this, I mean that the probability of measurement outcomes are really determined by intrinsic properties of the observed system. So here we really talk about systems, we talk about properties of system, and we pre-assume that these systems possess these properties independent and prior of our measurements and observations. So these are really statements of the reality per se, of the world per se. There is no place for measurement, and all these forbidden terms are really forbidden according to this viewpoint. And I can say that Einstein, Bohm, Bell, or one of the modern scientists, Speckens, supporters of this view. And then there is another view that actually all what quantum states tell us is this is some kind of a measure of observers' knowledge or belief about the results of future experiments. So you see that here just the opposite happens. All the statements are statements about our observations. There is no place to talk about reality, properties of the system. All what we refer to are observations and results of the measurements. So maybe John Archibald Virel or Rovelli, Chris Fuchs, and Anton Zeilinger could be put in this camp. Now, how we describe then this experiment according to these two different views? Again, quantum theory predicts only probabilities for individual outcomes. Now, first I will maybe say something about interpretations that refer to the knowledge. And before I do that, I want to say that there is a very uncomfortable situation with these interpretations for a quantum physicist, because there is no free lunch. Whatever you choose, either the first camp or the other camp, there will be a place where you have to pay. And it will be something which you dislike. And maybe if you talk about knowledge, then of course the first question that may be posed is whose knowledge? Knowledge about what? Does this mean that there must be necessarily observer present in the front of your experiment? What about when we apply quantum physics to the Big Bang, when obviously no observers were around? Does observer, and this is more in the words of John Bell, does an observer needs to have a PhD in order to observe? And what about an observer that had 2 shots of schnapps beforehand, before trying to observe? Okay, this question needs to be addressed. And although some of these questions could be addressed, I take here a neutral position, so I will not address them. The other thing is, what about the viewpoint about interpretation that refers to reality? And now I will, with the danger of repeating something which we heard in the previous talk, I will introduce so-called hidden causes. So what I mean with this is, according to this view that quantum theory should be about reality, you can say that, well, indeed, maybe these probabilities arise through our ignorance about the actual state of affairs. And in nature, there is no real objective probabilities. It's just due to our ignorance about our uncertainty, what really happens around us. And so you can think and pose the following question: is there a cause, and even a hidden one? I call it hidden one because we don't have this in quantum theory. It could be hidden. We cannot even maybe access these hidden causes, but maybe there are these causes, even hidden ones, that determine which outcome will be observed in an individual quantum measurement. And what I really mean that is that, well, maybe a particle carries with itself this hidden variable, and when the hidden variable is, for example, lambda plus, then this means that particle will always, with certainty, be detected in detector plus. And similarly, if the hidden variable is lambda minus, it will be with certainty be reflected and finally end in detector minus. Okay, so then, by the way, I mean, I was told that whenever you put an equation, you lose kind of half of the audience. But Professor, I think Milford was first icebreaker, and then Reinhold followed, so I thought you're still around, so maybe I should keep this. I promised there are altogether 3 formula. So this what I think is the way how would you think about probabilities if there would be a hidden causes. So this is a really probability to see the photon in detector plus. That's what you can observe. But then you say, okay, I really think that there is something in reality and there are hidden causes. And then I think that the whole ensemble of photons can be divided in some sub-ensembles, some of which carry the hidden variable lambda plus, and this is probability 1/2 in our case. But when they have this hidden variable, then with certainty they will end up in detector plus, and half of them maybe carry hidden variable lambda minus. But when they carry lambda minus, conditional probability is again 1, because they with certainty will end up in detector minus. So you will see that when you stick to talk about reality, there is a possibility to reduce probabilities to deterministic effects. So you really think that underlying there is a determinism. It's just I don't know, and that's why it appears as a probabilistic statement. If you stick to the other camp and say, no, quantum theory is not about that. It's only about the belief on an observer or knowledge about an observer, then you don't need to go into a deeper level. You just say, look, these are observable probabilities, and these probabilities are really objective. They are not reducible to anything deterministically. I really believe it's like that. There is nothing deeper than that. They are irreducible objective probabilities. And I have to say that these are really directly observable probabilities. So if you want to go beyond this, for whatever reasons, philosophical, ideological, in order to talk about realism, you then step into the terrain which is not anymore secure because these are not directly observable. Okay, so, well, people very soon in the history of development of quantum theory arrived, roughly, there are these two positions. And, well, at that time, it was also popular to shut up and calculate. And although I really admire Wolfgang Pauli, he was one of the supporters of shut up and calculate, at least at that time. So what he said about this dilemma, about whether interpretation that refers to reality or refers to knowledge, was following. One should no more rack one's brain about the problem or whether something one cannot know anything about exists than about an ancient question of how many angels are able to sit on the point of a needle. And really, that was the prevalent atmosphere in the foundations of quantum theory for decades until, and now I'm repeating here what Professor Bettelman said, until John Bell came to the stage. And I have to go to this also, and maybe it's not even bad to hear something twice or 3 times, who actually proved that local hidden variables, I'm thankful for you to introducing this, are in contradiction with quantum theory and with the nature, with our experiments. So all what remains, if you want to take the position of realist, to put it shortly, is that you accept a truly non-local influences, like it is the case of Bohmian mechanics, and I list Bohmian mechanics as one of the possible interpretations. So what it really means non-local. So we usually have, and that's the final slide about Bell experiments, we usually have these 2 characters, Alice and Bob, and they are separated from each other, maybe by 1,000 kilometers or more. And then each of them has some measurement apparatus. And this measurement apparatus has some switch. That's something the observer can control. So I can freely choose to put the switch in one or the other position. And then there are results of the measurements, which I cannot control. It's just answer of the nature. And then they share some source of particles, and one particle is sent to Alice, the other one to Bob. And just to put my second formula, equation, I have to introduce some notation. So I say the outcome of Alice is A, so it denotes whether one or the other lamp flashes, and the outcome of Bob is B. And I denote the setting, we say the measurement setting, this is the switch position as Y1 and Y2 for Bob, and X1 and X2 for Alice. And then what non-locality means is that Bob's choice of measurement influences instantaneously hidden probability for Alice's outcome. So the whole picture has only meaning in the hidden variable framework, in this deeper realistic framework, where I have these lambdas. And you see that this is a probability for Alice to see the result A. And this probability depends, because they are not the same, depends on what Bob has done far away. And that's what you have to buy. That's the point where you have to, so to say, pay for an assumption that you want to keep. The quantum theory refers to reality. So that's another set of problems you can face if you don't want to talk about knowledge. Knowledge itself has problems that I mentioned before. So It's important, however, to say that on the operational level, because these probabilities are hidden, we cannot measure them, everything is fine in the sense that these influences cannot be used to communicate with other people with velocity larger than light velocity. Okay, so this is the first experiment, and I have another one, a thought experiment, in which you can see how different interpretation try to explain them within their framework, and to see that there are always difficulties that you cannot avoid. And the other one is so-called, well, Schrödinger's cat experiment, and Schrödinger himself introduced this in 1935 because he was not pleased with the, at that time, situation of quantum theory, and he called, well, a ridiculous case, the case of his thought experiment with cat. And, well, what is it about this experiment? And you surely heard that many times. It was popularized, always it's popularized in books and in journals. Well, you have a box, and in a box there is a cat, there's a flask of poison, and a radioactive source. And everything is sealed in this box. Now, the mechanism is such that if and there is a single, maybe, atom that can decay or not decay. Now, if the atom decays, there's a mechanism that breaks the flask of poison. The poison is released and kills the cat. If it doesn't decay, it remains undecayed, then nothing happens and the cat is alive. Now, you're all familiar with lifetime of a decaying particle. So if you have, this is a time after which a half of a nuclei will decay. So if you have a kilogram of radioactive substance, after this half lifetime, a half of kilogram will decay. Now imagine that you have only a single nucleus that will decay. Then after this half, or exactly the half lifetime, you will not know whether it decayed or did not decay. And all what you write, and this is my final formula today, is something like that in quantum mechanics. This is a so-called quantum superposition, again a psi function in which you have these two possibilities, namely atom decayed and cat dead, and atom undecayed and cat alive. Now, if you look, and if you don't know even anything about quantum theory, the notation itself should suggest to you that it's neither of these two well-defined states. So it's neither atom decayed or cat dead, nor it is a well-defined state atom undecayed and cat alive. It's something else. Now, the people who really believe that quantum theory should tell us something about reality have a problem with this, because who has ever seen a cat which is neither alive nor dead? And Einstein was very much concerned about that, and 15 years after original proposal, he wrote a letter to Schrödinger, and I read it because the small letter. So, you are the only contemporary physicist besides Laue who sees that one cannot get around the assumption of reality if only one is honest. Most of them simply do not see what sort of risky game they are playing with reality. Reality is something independent of what is experimentally established. Their interpretation is, however, refuted most elegantly by your system of radioactive atom, amplifier, a charge of gunpowder plus cat in a box. So he put even gunpowder to make it more dramatical, but it's not important. In which the psi function of the system contains both the cat alive and blown to bits. Nobody really doubts that the presence or absence of the cat is something independent of the act of observation. Okay, so now this is the state of the art. That's the quantum mechanical description, the state that I put on the previous slide. Now let's look what different interpretations have to say about that. So the Copenhagen interpretation. this is all based on the most serious source, Wikipedia. I adapted this a bit to my taste, but I have to actually acknowledge that it's quite a good description to my taste. So anyway, so while the box is closed, the system exists in a superposition of the states decayed atom, dead cat, and undecayed atom, living cat. And only when the box is open and an observation performed does the wave function collapse into one of the two states. So what really they want to say is, as long as the box is closed, there is indeed this state, which is neither dead nor living state. And it's a kind of a new feature of the cat. It's a new state that we don't know what it really means, maybe, because we are used on the everyday life and classical like states. But it is a new feature of the state. And I kind of sympathize with this because and this is more now to the physicists when we talk about spin up 1/2 along x direction. When we write it down, we write it as a superposition over the spin along z direction up plus spin along z down. And we don't say, well, this is simultaneously both. No, it's a new quality. It's a spin along x direction. It's just the way how we write down. Now, this is also a new quality. So, but however, when we open the box and we interact with we make an observation, and this is what quantum theory predicts, we find only one of these two cases, and that's why we talk about jumps into the eigenstates, or projection of the state, or all these technical terms, which only mean that you will find one or the other case with the same probability. Now, there is then objective collapse models. This is, well, the people who sympathized with this viewpoint actually want to say one or the other concept from the classical notions of reality. And they would say that according to these models, superposition will be destroyed spontaneously in the box, even without opening it. So it will, irrespectively of external observation, that superposition is destroyed when some objective physical threshold, for example, a very large mass or very complex system, are reached. So even if you want to make a superposition of this cat, prepare such a state in the box without opening it, you will fail because the laws are modified and you will not be able because you cannot reach by law, physical law, it's forbidden to make such a ridiculous cases. So they excluded by fiat, actually. And they are not in interpretation, and as I indicated at the beginning, it's really modification of quantum theory, because quantum theory tells us you can put in a superposition whatever you want, even the cats. And so if you want to save somehow very dramatically this belief that every state should be a well-defined state according to our classical notion of reality, you should forbid it. Okay, and that's one way out. And in any case, experiment can decide between quantum theory of that point of view. But then there is something which I haven't mentioned so far. Okay, and it also belongs to the first camp where quantum theory refers to reality, and that's so-called many worlds interpretation. And it's a very radical one. It says that both alive and dead states of the cat persist after the box is open, but in different worlds. And these different worlds actually do not communicate with each other. And if you need a picture of that, it looks something like that. Yeah, you have this cat in a box. And, well, whenever we open the box, we will end up either in one or the other branch of the world, namely the cat is dead, for example. I open the box, the cat is dead, but according to this interpretation, there is actually a parallel world where I opened the box and the cat was alive. And so when the box is opened, the observer and the cat split into, well, two worlds. An observer looking at the box with a dead cat and an observer looking at the box with a live cat. Now, there are some of you that probably heard this for the first time. And if I think very carefully about that, I would be completely shocked that a serious scientist can tell something like that. I mean, really, it really sounds completely like these crackpots. Nevertheless, very, I mean, even I think in this foundation's predominant interpretation among the theoreticians is that one. And the person who actually established quantum computation, that's David Deutsch, is one of the strongest supporters of that. And actually, he claimed that he came up with an idea of a quantum computer thinking about parallel universes. I mean, this is, if not, this is a stronger evidence that that exists to me. Well, what it says is whatever can happen will happen in some of the universe. So, for example, you meet a girl with a red dress, and then turned out it's very disappointing. And then you meet another one with a blue dress, and I mean, you roll down this. It's quite depressive. This line is quite depressive, but maybe if you're lucky, you can climb up a little bit. And so the guy who actually introduced this didn't call this many worlds, and he was much more careful in defining this. He noted this as a relative state formulation. It was a Hugh Everett. That was his PhD. And then he presented this in 1957 to Niels Bohr and colleagues in Copenhagen. And there is a very sad story that actually the acceptance of that was really, they were quite cold, and they didn't like it. And eventually he gave up physics. But yeah. It's a very wild, very interesting idea, where you still can keep and talking about realism. Okay, and then there is something I didn't talk about that much. There is this, and I mean, Copenhagen, quantum Bayesians, and relation interpretation, which are quite similar, and they indeed refer to observer's knowledge. And I think one of the most radical of this is, in a sense, relational interpretation by Carlo Rovelli, in which he actually allows that different observers can give different accounts on the physical situation, depending on the information they have about the system. Okay? And I must warn you that this doesn't mean that there is something happening in the world. There is a fact that is unique for everybody, and some of us do not have the full information, and the others have maybe the full information, or we have different pieces of information. It's not about that, because then still you will talk about reality. It's just our ignorance of what has happened. It's a much more radical view. It's the view that even what we call a fact or an event could be different for different observers. Okay, so it's a much more radical step in this. And according to that, well, before the box is open, the cat has information about the state of apparatus. The atom has either decayed or not decayed. Okay, but of course, if it decays, it has for a millisecond this information, but you can replace poison with food, for example, and then the cat is hungry or it's not hungry, but you understand what I want to mean. So the cat has this information about whether the atom has decayed or not decayed, but the experimental describes not the atom itself. The experimental describes the whole thing, the box, as one single entity, and in that sense it describes both the cat plus the apparatus. So what the external observer describes is simply a different, let's say, system than what cat describes. And they may have some complementary observation. They can associate different states. For example, the cat maybe describes, well, the cat maybe knows that the atom has not decayed. But the external wall is not even interested in this, doesn't even describe the atom itself, but it describes the whole box, the CAD plus apparatus. And has another piece of information, not about the atom. The system even he describes is a different one. And now, if you assume that all observers are equally valid, there is no preference to one or the other, so there is no one truth, much like in the Rashomon effect. So there is a kind of frustration with this situation because we do not have a consensus of what the theory means. And furthermore, the possible interpretations are really different in their nature. And so what can we learn out of this frustration? And one possible path that I actually followed for a couple of years is that maybe there is something intrinsically deficient in the very idea that we should look for the meaning of physical theory exclusively on the basis of its formalism. What I mean with this is we start usually with quantum theory. That's a very close, nice mathematical or formalism or physical theory. And then we try to find out the meaning for the individual symbols of this theory. But maybe there is a more radical step. And maybe we can try to extract the meaning along with extracting the formalism or deriving the formalism from some deeper physical principle. What I mean is there are some axioms of the theory, much like we have in the theory of relativity. And these axioms maybe can help us to extract the whole formalism. So going a step back and say, well, I need some, maybe not even physically plausible axioms of the theory. When you look back, why should it be plausible that light has the same velocity in all reference frames? I mean, we just got used on that. It was a very radical idea at that time. So maybe we can even start with some non-plausible axioms and derive the whole theory out of that. And then when you ask me what it means that the Bell inequality is valid, I say, sorry, but I mean, it's because of these axioms. I cannot go deeper than that. And now there is, in the meantime, plenty of reconstructions of quantum theory. We call this reconstruction of quantum theory because you're forced to start with the concepts that are as simple as possible. So you don't have any technical terms that we are used in quantum theory, like self-adjoint operators or Hilbert spaces. And out of these axioms, we try to reconstruct the whole theory with full formalism. Well, it was a half of a success, this whole attempt, because at the end of the day, it turns out that these axioms were not really plausible in a sense that, not in the sense that that I said before, you know, even the language that they used were not of the level that we are used on in the theory of relativity. So they do not use Hilbert spaces, they don't use self-adjoint operators, but still they are really, to some extent, contrived. And not much of the physical insight come out of it. So I said so out of this frustration, we came up with this attempt, but the attempt turned out so far not to give satisfactory results. Okay, so we are back to the Rashomon story. And well, instead of the conclusion, I can offer you the following. So if you're not convinced with the many worlds interpretation, then you should know that there exists a world in which you were convinced by this story. And the opposite. Well, if you are convinced, there's certainly a world in which you are not. Or the other thing, you can believe in a relational interpretation. Then the truth is in the eye of the beholder. And with this, I would like to thank you for your attention.
Well, I see 1, 2, and 3, 4 questions here, and 5 even.
When you were introducing the hidden or the local variable, you were introducing it basically as an intrinsic property of this certain particle. And what if we assume that it might not be an intrinsic property of this particle, but it actually gets constructed by several factors, not just the particle itself, but also the interaction of the particle with its environment. For example, the mirror as an obvious example. Would that still mean that Bell's inequality would be violated, or what would be the consequences of that?
Thank you. In a sense, this is quantum theory, what you're saying, because when we talk about this, when we assign the state, we assign a state to a whole experimental context, including the mirror and the source and the place of detectors. In a sense, there is something inherently, if you want, non-local in the quantum theory itself. But the step for the local hidden variables was to break this chain and say, well, if you want to still say there are intrinsic properties, then you have to say that it's intrinsic properties even of totally non-local experimental arrangement. And any attempt to say, no, it's just intrinsic properties around the particle and maybe a little bit more, but certainly not that big, such that there is, I localize this around the particle such that there is no influences, no mechanical explanation of this non-locality. So in a sense, quantum theory is something what you want to say, that there is intrinsic property but of the whole experimental apparatus. But look, you have to imagine that we can have an experiment with 2, 3, 400 particles distance from each other. At one moment, you have the entire universe. And we have to, there is something non-local. You cannot be able to divide it in subsystems.
I actually have 2 questions, but they're rather short ones, so I hope that's okay. So one would be, is there any way of experimentally deciding between the many worlds interpretation and traditional quantum mechanics, similarly to the experiments we have seen that decides between Bohmian mechanics and quantum mechanics? And the second one would be, concerning Bohmian mechanics especially, but also about alternative interpretations, has there been any theory that was successfully reconciled with special relativity?
Of these hidden variables, you mean? Or
No, not just Bohmian mechanics, for example, as far as I know, reproduces non-relativistic quantum mechanics, but I have so far never heard of any relativistic theory that produces the same results as quantum mechanics.
Yeah. Okay, so interpretations are by definition something which are not distinguishable in an experiment. However, there are some papers, even recent ones, claiming that you can design an experiment that will be, for example, in favor of many worlds. But very often, people want to disprove a specific interpretation, let's say Copenhagen or whatever, and then have a very specific opinion what it really means. And then the whole discussion, the dispute starts with what it really means, one or the other interpretation. But I think that there is a progress, and we can somehow, there are more and more requirements on each interpretation in order to still make it all consistent. And maybe at the moment we don't even know, and we think that these are really interpretation. And these new ideas usually involve something like a Schrödinger-Cat state. It involves, or more precisely, something that some of you are familiar with, Wigner-Friend situation, where one of the observer is still described using quantum theory by another external observer. And then there is people try to make consistency between the statements of different observers and so on. So I think we are making progress in a sense that if you want still to keep consistency and maybe agree with what quantum predictions are, because we don't believe that we can soon make such an experiment, that we have to be more specific on what happens within certain interpretations. What does it mean? We're now collapsing a wave function and all this stuff. And the other one, I'm not familiar. I mean, do not work in Bohmian mechanics. My understanding that every non-local hidden variable would have a problem with preferred reference frame or problem, or have to assume that, because if you think that any correlation is established by a real interaction between A and B, and you can have different frames of references, where in one frame of reference A happens before B, and then you think, okay, A sent the information to B to establish the correlation, but in another frame of reference, B was before A. And then the only way to reconcile this, no, there is one reference frame in which it happens, and all others are just transformations. And that's what we kind of dislike, and there are difficulties, obviously, to reconcile this with relativity.
I want just to make a remark on the Schrödinger's cat experiment. For me, this is not so hard to find a solution, explanation for this, because of course there is this distinct moment when the cat dies. And from this moment on, it divides this after and before, and the states are probability one. This is like this mirror experiment when you have before this superposition. From this one side of the equation, and on the other side you have this probability one. And it means as soon this happens, then you know about the states, and as long as it doesn't happen, you have this superposition, the description. And it's not, I mean, this multiverse is like Gedanken experiments, it's like this thought experiment, and I can only accept the multiverse in this sense that you think when you repeat this experiment over and over, you get more and more results. But it doesn't mean that this is a time-coherent multiverse. But I mean, when you repeat it, you're starting this T0 or T null, and then you have this, and this is creating this multiverse. So I mean, repeating this experiment 100 times is giving you 100 results, and this is kind of multiverse. And time and space is an illusion. And I think the fact where you see this is that A and B are changing their states even long distances from each other instantaneously. And this shows you that this, what we think that space or a distance is, cannot be as we think of it. So, I mean, there must be some kind of connection. But I mean, this is the same like this multiverse. It's hard for us to understand, but I mean, we have no chance to understand this, and this is what Popper comes into, so we have no chance to see the real world. So for us, this is this superposition state, but in the end, it's definite states, and that's all.
What do you think about the synchronicity theory as Thomas?
Yeah, but I mean, dreams are not real, yeah? But I mean, a dream is giving you this a star reality, yeah?
I just want to say that I try to be neutral, so I didn't want to say my opinion, my preferences. So I sympathize with many what you said.
So basically, it's concerning your objective collapse presentation. It's maybe just like a technical comment, but if you admit as a criteria irreversibility, using some definition, couldn't you just use like standard quantum mechanic? Basically, by admitting irreversibility, you're asking that all the systems should be open. So effectively,
I think that it's a matter of principle. In every, for all practical purposes, I use this forbidden word by John Bell, this will be irreversible, and you will have what we technically say decoherence, even within quantum theory. And at the end, the cat will collapse, even without opening this maybe, if there is a leakage, even infinitely small leakage of information out of the box. So it's very hard to isolate this. But it's really a matter of principle. I mean, every collapse model has to introduce some free parameter coming out of nowhere, because simply I don't like cats in superposition. So I like neutrons in superposition, but I don't like cats in superposition. And then you have to fine-tune these parameters such that both are okay. And so they put some parameter. And now it's the matter of experimental techniques and to really try to achieve this, that it still can beat this. But of course, in every real experiment, you will have some decoherence and leakage of information. But if you can beat it, you will exclude this, and then they will put another, sorry, it was not this number, I want a little bit higher, and so, but at some point there is a room, they cannot be higher, they cannot go into it, definitely, because they want superposition of atoms, for example.
Okay. At first, thanks for the nice talk. And my question is about another forbidden word, the observer. So in the cat example, we have the observer which observes the cat. What if we put him into a box and let someone observe this box? So who's the observer? What's the observer? What's that? I don't really get it.
No, that's a very good question, of course.
Sorry.
Now I have to say something what I really think. So when you write down a wave function or a state, I really think this refers to observer. And this observer doesn't need, of course, to be present. I mean, nobody clear in his mind will require that quantum theory is only there when we are there. However, quantum theory is maybe theory that is tailored to tell us what happens if there is a hypothetical observer who will do that and that. Then you make some predictions. So that's first level. So I do think that it refers to an observer. So now you have a different levels, just as you said. The cat and the system for the cat is just an atom. So it will write down a wave function of an atom. The guy who put this in closed box has a different level of description and will write exactly the state that I wrote. It's an entangled state between the cat and the atom. But then there yet could be another level of a super observer that has bigger project money and budget and keep even this observer and the cat and atom isolated in his kind of a new box. And well, if there is no principal limit, then it's always the limit of the budget that will define who writes which state. And indeed, if you write, I think there is in principle maybe infinite regression in that sense. That will be a relational kind of interpretation in which all of them are correct. There is no reason why they shouldn't be. They just refer to their observations. But these statements of all of them cannot be put together in one unique reality, because we will get back into real picture.
So, due to our very prolonged time now, we will close this questioning session, and maybe people can discuss among themselves later on, and hopefully people take in more thoughts from this event and be able to discuss and contemplate more. For some closing words, I refer to Flavio Del Santo.
Yeah, thank you. Just briefly, so I'll leave you to go home. So I want to thank you so much for being here, for having me here the whole day. It was a long event. Thank you so much for the speakers. We have listened very amazing talks, approaching the problem. We have addressed it from very different perspectives. I hope you really learned something and that we could stimulate something to be further inspected. I think that the great participation of today actually has found the interest of so many people, because there actually is a needing of more fundamental thinking in science. And I've seen people from the master program of History and Philosophy of Science, and people from the master program in Science, Technology and Society. So I would just expect that this is not a unique and lonely event, but we can organize something more and continue in this direction of a broader comprehension of all the subjects together without this arbitrary distinction. I think I opened the symposium telling that this lack of fundamental questions is a worldwide problem, but I also think that Vienna has a very fertile ground to rebuild the connection between philosophical approach of science and to social and historical contextualization of sciences. We have mentioned so many times the Vienna Circle, Karl Popper, the Mach-Boltzmann debate, and everything happened in Vienna in the last century, and we should try to restart from there a bit and trying to keep it a bit more alive, this kind of critical thinking. And in this direction, not to keep it on a very abstract level, I invite actually the students of all the faculties to also attend the courses from other faculties. For instance, in physics and in science, we have a compulsory module of soft skills, which via asking the SPL can be done via exams in different faculties like History and Philosophy of Science or STS again. So I hope that we can have more events, more activities. Approach us. We have this discussion group called Naturwissenschaftscafé. We have a website. Write us if you want to be more engaged in this kind of activities, and we can try to put it forward. Thank you so much for being here, and I hope to see you again soon to something similar to this. Thank you.
So since I'm the only who has the microphone, I want to thank the organizer. I also already told them that after this successful event, they are now in the trouble, because every next event that we want to organize, we will get...
We need a bigger venue there.
Yeah. So thank you very much for all what you have done. It was a great event. Yeah.